Hey, this is a description of the second assignment for FCM 708 in the fall of 2014. And the nature of this assignment is going to have to do with virtual memory, which we talked about a little bit in class today. Um, so, virtual memory is a way to let a process sort of view its own memory as being contiguous while in reality, different parts of the process's allocated memory might be spread across different regions of main memory, or maybe even in other storage media like disks. And this week during lecture, we're going to talk about how that all works. And I'm going to give a little bit of a preview of that lesson now, just to help explain the program. Um, so the maybe you can start with this picture. Um, so if I'm also going to draw a picture of my own. So here's how a process sees its memory. It sees it as one big contiguous chunk. And I'm embarrassed because I can't draw a straight line. Let me turn this on. So this is the process memory, and it sees it all as being, just from 0 to whatever its maximum address is. And so each entry here is, some addressable location in memory, like here's an addressable location. So instead of just viewing this as however many addressable locations there might be, I'm going to break it down into blocks, all of the same size, called pages. So this is going to be the first page here. And it doesn't matter, or it's at least, variable addressable um, how many addressable slots go in one page. I think in reality, like a typical page could be like 4 kilobytes. But let's just say that a page is 5 addressable locations. And this process will own a certain number of pages. So, from the process point of view, it can also think that it has more memory than is actually available on the entire system. So this is sort of it's going to be logically as if the process's memory looked like this. And it doesn't in real memory, but the programmer and the process can act as if the memory really were organized this way. So here's the second page, page 2, and I think I accidentally put 6 in here instead of 5, but so please forgive me for that. All right. So because of this organization, a process can refer to some memory location as an ordered pair. And maybe I should have called this the 0th page. But let's just say the 0th page is if you want a 0th page, it's north up off the screen. So if the process wants to, let's say read from this location in memory, so it's viewing this red location as like 0x44FF2BBBC1 or something, it can refer to it as an ordered pair. So the red memory location can be represented as an ordered pair. I guess I mean an ordered set of size 2. Let's say P, D. So P is going to stand for page, and D is going to stand for displacement. So this is page as in notebook page, not as in Jimmy page. And this is displacement. Oh my god, that color combination is wonderful. So for the red place in particular, it's on page 1, and the displacement is this would be 0, 1, 2. So the ordered pair 0, 1, 2 equals where the red dot is. So now if the process can, the way we're going to talk about this in much more detail. So in the hardware, there's not special software, there's not special hardware for representing an ordered pair. It's just all one big binary number, 0011, 001, 0011. And it just happens that, let's say, the first two bits are dedicated to describing D, and then the remainder are dedicated to describing P. And there is a whole philosophy between trade-offs related to making D take up more of the available space and making P take up more of the available space, and we'll talk about all that stuff in class. Yeah, and if this was actually supposed to represent that ordered pair, then this would be a 0 and this would be a 1. Okay, so this is how the memory address might be represented. And so how does that get translated into real memory? So let's say that there is somewhere over here, there's real memory, which may be shorter than the memory that the process thinks it has. But the real memory is also kind of organized into pages. We call these page frames. So here's page frame 1, here's page frame 2, and page frame 2, and here's page frame 3, and so on. And this is supposed to be real memory. So just like in the process, the page frame consists of 5 slots, and it's not necessarily 5, it's just 5 in this example. So 1, 2, 3, 4, 5. So here are the 5 addressable locations within a page frame. So let's say that we want to translate this virtual memory address, which we think of as the ordered pair 1, 2. So here's the virtual address. We want to translate that somehow into a real address. And the way we do this is through something called a page map table, or just a page table. And this picture is getting kind of busy. Maybe I should zoom in. Whoa, okay. So now I've got some extra space here. So there's something called a page table. And the page table belongs to just this process. So we didn't give this process a name, but it might very well have a name, such as, Balthazar, whatever. And when we had class last time, we talked about processes having records stored in memory and referenced by the operating system that describe sort of everything about them. And those were called PCBs, or process control blocks. So the process control block for this process knows the address and memory of its page table. And so I'm going to have more to say about that when we start talking about the actual project. So here's the page table for this process. And the operating system, when it loaded this process on the processor out of the PCB, it retrieved this special information about where this particular process's page table is located. Now the page table is just a map between the virtual pages and locations in the real page frames. So this page table is going to have 2 columns. One is for the virtual pages, and let's just call those, remember 0 is off screen somewhere. Here's 1, here's 2. So in the left-hand column is sort of the domain. That's going to be the the virtual page, and over here there's going to be the corresponding real page. And let's say the corresponding real page for page 0 in virtual memory is, I don't know, 22. And let's say the real page for virtual page 1 is page 2, and the real page for virtual page 2 is page frame 14. And let's finish translating this virtual address into a real address. So it's saying that it's at virtual page 1. Now in the page table, we go down to the entry for virtual page 1, and it says that that's associated with real page 2, which is this guy. And there's also an offset here, which is 2. So here's 0, 1, 2, 3, 4, and then there's 1. No, that's 5, isn't it? Okay, so 0, 1, 2, 3, 4. So there are 5 slots here. And so it knows that the red dot is supposed to go in virtual page 1, which becomes real page 2. The offset stays the same. The offset is 2. And so that means that the red dot ends up right here, because this is 0, 1, 2. So that's where the red dot ends up in real memory. Okay, so I think that's all the background that we need for the time being. But let me show you a better picture, or I think we got a peek at this before. So this is from Jin Woo's lecture notes, which might be the same as Shamik's lecture notes from years ago. I'm not sure. What this is showing is, the CPU is in this picture. I guess that just is supposed to give you the idea that hardware is involved here. Hardware is involved because all this stuff has to happen extremely quickly. And this is supposed to be the page table for this particular process. It has virtual page P, and so virtual page P is associated with real page F, and the physical address becomes FD. And with paging, when you write them next to each other like this, it's really just concatenation. So, F can be some hex or binary number, D can be some hex or binary number, and the real physical address you end up with is the actual address that comes just from writing those two numbers right next to each other, which is kind of cool. So that is that's efficient. That doesn't even require an addition, so it happens pretty quickly. And here's another picture of the same thing. So this is the logical memory of some process, and this is just made up data for what the page table for this particular process might be. For this particular process, the 0th virtual page is associated with real page 1, and you can see right here that's where it is, living in real memory, and its virtual page 1 is real page 4, and its virtual page 2 is real page 3, and its virtual page 3 is real page 7. Here it is down here. And you might you might be wondering what the point is, because it just seems to be scrambling things around. So, but remember, not all of these. There might be more virtual pages than there are real pages, in which case some of the pages might be off on the hard disk, and then they can be paged in as necessary, and it allows the process to think that its own memory is contiguous, which can be helpful. You really don't want to worry in your program about how the code for your program might have been compiled and embedded into the computer memory. That would be incredibly complicated. So that allows you to make allows you to make the simplifying assumption that the memory is contiguous. And also, because some of the pages might be off on secondary storage, it allows the memory to be logically bigger than it is physically. And this is basically the same as before, except now it has ABCs and stuff. So you can pause the video if you find that picture attractive. I'm going to go on now. So this is still pretty much the same picture as before. There's something new, which is a free frame list. So somehow you have to know which physical frames. Let's say that when a new process is being loaded up, or what's the fancy word, dispatched, it's going to need to allocate some memory for itself, and so we're going to have to construct somehow a page table for this process that maps its virtual pages into physical memory. And it would be nice if Archangel Michael came down and just provided it, but the operating system has to figure out what it should be and actually build it. And one way to do that is to maintain somewhere a list of free page frames, and that's what's going on in this example, and that's what I plan for us to do in our simulation. So in the free frame list now reflects the fact that there are all these frames that are unoccupied. 16 and 17, these ones that are like azure or cerulean or whatever ugly blue color this is, those belong to some other process. And right now in this picture, the pages for this new process haven't been allocated yet, but we know that these are free. So it's telling us what the gray ones are. The gray ones are 13, 14, 15, 18, and 20, and here they are, plus 15 in some scrambled up order. So we use those, we just pop them. It looks like it's popping off the top, right? 14 gets popped off the top and assigned to virtual page 0. 13 gets popped off the top and assigned to virtual page 1. 18 gets popped off the top and assigned to virtual page 2, and 20 gets popped off and assigned to virtual page 3. And now you have the virtual memory mapped into real memory like this. I don't think there's anything awesome on the next page, but let's see. It's just talking about hardware stuff. So I don't want to talk about anything more than we need to actually do the assignment. Now, I've written a program that simulates activity that a virtual memory system might have to deal with. And here is some simulated activity. So maybe you're the memory management unit, and somebody creates the process P0, and it requests 3 pages of memory, and then it sets its virtual memory address page 1 displacement 2 to be the letter A, and then P0 gets destroyed, and now we create a process P1 and it requests 2 pages, and create a process P2 and it requests 2 pages, and now we want to set the virtual address 04 to be equal to B for process 1. So if it looks like it's just randomly doing things, it is just randomly doing things. I'm going to go through the code and talk about how the activity simulator works in a second, even though it's not something that you have to worry about. So what you have to do is build a memory management unit simulator that deals with all of these requests and keeps things straight in main memory, which in your simulator will just be an array or a list of a certain size. And then after all the activity is done, your main memory has to look right. And I've made some examples of and I've also worked kind of hard on debugging my program, so I'm fairly certain that my examples will be the right answers, and then you can, as you debug your code, you can compare it to what I say is the right answer. Alright, so let's look at the activity simulator, and I'm going to give you this code. I'm going to give you some activity texts. I've made several of them. I've got one that's kind of long, it's 100 entries long. I've got one that's sort of short. No, that's not it, sorry. This one's kind of short, it's only a few lines long. And I made one that is medium, and I think this one is 20 lines long. So we can use these for debugging. And the activity simulator takes an argument from the command line. So this is just saying, give me my command line argument, bozo, or I'm out of here. And this says that the number of simulated lines that we're going to output is just what the command line argument is. So the command line argument specifies how many lines of simulated output. And because it's creating and destroying things, I don't want to destroy something that isn't really there, and I don't want to set something that isn't alive. So I'm keeping track of which processes are actually living. And I think this, yeah, this counts the current line. So initially the current line that we're about to write is line 0. And these letters are just, you know, the values that are getting put into memory kind of randomly. You can see that they just go A, B, C, D, E, F, G, and then they loop around when they get to Z. And I made a module called process, and inside of it is this class called process. So talking about object-oriented stuff, which is classes, is outside of this class. But let me show you this file anyway. If you don't understand it, that's okay, because you don't need to. So this process is just a thing, and so this is where the page size gets specified. This keeps track of how many processes exist in the world. And when you create one of these things, it takes a name as input and also the number of allocated pages. And then it increases the number of existing processes by 1. And you can set the page size. I've never used any of that stuff. So it's basically just a struct. If you're familiar with C, I would have made a struct if there were structs, but there are no structs in Python. So here's create process. You know, I don't think it's taken a while to go through this, and I think I might just be wasting your time. If you want to know how this works, you can read it, and if you don't, then don't bother with it. But one thing that is important is this. Because global variables work a little bit differently in Python than I thought they did. So the way they work is actually kind of crazy. So I've got a variable called cur letter up here, and I want this to be a global variable for my program. So I want to modify that in all of these different processes that all these different functions that I have. And I want it to be the same variable, so that if I change it down here, then it's the same as changing it up here, even though I only seem to use it in this process. But it turns out that in Python, the way you do that is, so if you just read from the variable in here, then you get the global value. But if you just start writing to it without this line, it creates a local variable with the same name. So that kind of surprised me. So if you're using a variable, you want it to have global scope, and you're going to write to it. Then before you write to it in your program, you need to put in a little line that says that you're going to be using it globally. Okay. So I'm going to show you some of the code from my solution, and I'm gonna pause the video because I don't want to give the game away like I did last time. So here's the top part of my VMSim Python program, and I just wanted to show off how I'm doing some stuff and maybe give you some ideas for getting started. Don't want to show you too much, but one thing you should do is keep things like the size of the physical memory is as a parameter that you should set in just one place. So you don't want to have 40s scattered all throughout your code. If you want there to be 40 physical addresses, then you should define that in just one place and call it memsize and use it globally throughout your program. Similarly, if you want the page size to be 4, you should set that in just one place and not have a bunch of 4s going everywhere. And so here I make main memory as just this makes it 40 empty strings. And so I'm building the free list. Let me remind you what the free list is. The free list is this thing that tells the system which page frames are free. And so this is my version. It's just going to be a list, of course. And you don't, once you pick these two numbers, it's determined how many pages there are. There are mem size divided by page size page frames. And so you need in the free list an entry for each page frame, and so there are this many of them. And now what I'm doing is, I just thought it would be boring if the free list always came in standard order, like 1, 2, 3, 4. So I'm sort of randomizing it a little bit. And what I'm doing here is I'm just basically randomly popping things off of this, which is the numbers 0, 1, 2, 3, 4. This is 0 through this number, -1. And I'm randomly popping off these digits and then appending them to the free list. So the free list for me is just the first, in this case, 10 numbers, but they're coming in random order. But it's not too random because I'm seeding. I guess I haven't explained this in class, and it takes a while to explain what it means to seed the random number generator. But because I seed it, it is producing random numbers, but it always produces the same random numbers every time I run the program, which is, you should do that too because it makes it easy to debug. So it's not really that I want things in random order every time, I just want things to come in some kind of arbitrary order. Alright, and what else have we got? So I manage my page table in this kind of crazy way. If you don't want to do this exactly, then you don't have to. Your main memory should look the same at the end as mine, even if you decide to take a different approach. By the way, I've been saying a lot of information for quite a while now, so you might need to take a break. If you do, you can always just push the pause button and go get a soda. I accidentally bought some pretzel M&Ms the other day. Those are pretty good. You could go get some of those. So what I do is, instead of having one page table for each process, I have one big page table, and every process is associated with a certain offset within the page table. And this dictionary keeps track of that mapping. So like if the first process allocates 3 pages, then that means that in the page table, the first 3 addresses are going to belong to P0. Then he gets destroyed, and now P1 allocates 2 pages, so the first 2 pages belong to P1. Now pages 3 and 4 belong to P2, and when I send P1 into this dictionary that translates process names into offsets, it's going to return 0, because the offset of P1 inside the shared page table is 0 because he owns the very first 2 pages. But the offset of P2 is 2 because the pages that P2 owns in the shared page table begin at 2. So to use this dictionary, which I build and maintain, I type in, or I send in the process name, and the offset comes out. And I have to say that to explain where my simulated output is coming from. Here I don't think it's too naughty to show this is a function that I use to print out main memory. And this is kind of a nice thing, the enumerate command. It's like instead of just doing for p n pages, you can do for ip and enumerate pages, and then you get the index as well as the element, which can be useful. I'm using it like this. Um, so I can say that I'm printing the ith page and then print the page, which is P. And then at the end I just do the raw memory dump. Alright, so now I'm going to show you what the output of my program looks like, and I'm going to pause it so I can set that up nice. So in this directory you can see this is my virtual memory simulator, and I've got several sample output files. I'm going to give you all of these, and I'll make more of them if you want me to. So let's look at this one, sample out 0. Sorry, it must not have existed or something. .text. Okay, so this is the debugging information that my program generates, and this is a pretty complicated program, and you'll find as you get, if you already have experience programming, you already know this, but you'll find if you aren't experienced, as you get more programming experience, that debugging, printing out information about what your program is doing is really crucial. You know, you'll think, oh, I programmed it to do this, so it's doing that, but that little bastard is not doing that. You've got to get it to print out the variable so you can see what it actually is doing. So first we start the simulator, and this line says which of the activity files it's simulating, and so I've got this activity file called short activity.txt, and this is the content of that file, and this is the output that my program produces when I simulate those actions. So the main memory size is 40, the page size is 4, so there are 10 pages. So the page table has 10 entries, and this is what the free list looks like initially. By the way, if you decide that you want to use exactly my approach, and you want your output to look exactly the same as mine, you should be able to sort of copy and paste my free lists from the sample data, and then everything really should be the same. So this is what came up randomly when I shuffled the free list around. Okay, and so the way allocation works for me is I really do pop off the free list. So 5 is allocated first. So what happens? You create this process P0, and he wants 3 pages. So off the free frame list, I assign the real memory page 5 to P0, and then the real memory page 7 to P0, and the real memory page 2 to P0. And you know, for me, I have a shared page table, and the offset of P0 is 0 because his entries begin at 0. And then there are some set commands. So this memory location, so 0th page displacement 2 becomes A, then 00 becomes B, and then A gets overwritten. So let's translate this into, oh, this one has always on top, sorry. So let's draw a picture of what's happening there. Okay. So let's look at main memory. So we have the page table, and we also have P0, and P0 has some pages, so he has 3 pages: page 1, page 2, and page 3. And each one of these is, you know, 4 slots, because I have the parameters set so that right now there are 4 addresses inside every page. And we have to look at the output a little bit to see what actually happened. So first he puts, so let's look at what happens in the page table here. So page 5 gets assigned to his virtual address. Oh shoot, I should have started at 0. When will I learn? Fool me once, shame on Okay, so page 0, page 1, page 2, and so his virtual page 0 is associated with the real page 5, and his virtual page 1 is associated with the real page 7, and his virtual page 2 is associated with the real page 2. So there was a weird little collision there. Okay. Now he does some setting, and let's see if we can scroll down a little bit. So in page 5, so what does he think he does? He thinks that he sets into 0, 2, he puts A. Oh, that's so irritating. I'm really sorry that keeps happening. So here's 0, 0, 0, 1, 0, 2, he puts A. Now what does that really do? So his page 0 is real page 5. So in main memory there's 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. So here's page 5 in real memory, and it has 4 slots. The page frame looks just like a page, and he puts A there, but really what happens is A goes here. And then he thinks he puts B into 0, 0, but 0, 0 is really 5, 0, and so B goes here. And then he thinks he does 0, 2 equals C, so that's the same slot. He changes this to be C. But what really happens is that this gets changed to be C. Okay. And now he gets destroyed. And the way my program works, that wipes out all the... I delete all of his entries from the page table. This is a little bit of a... My approach here with the page table is frankly a little bit tricky. And I want to maintain it as a constant length, so if I delete 3 things, which you can do, just take a slice and then for each element of the slice use the remove command to remove it from the list. But for everything you remove, you need to add an empty string to the end if you want to maintain it as a constant length. So now the page table is empty again because he's been destroyed, but this is still in main memory. And P1 gets created with 2 pages. So let's look at the details of the birth of P1. Oh, by the way, this I also put in debug for the destruction. So I say that he did own 5, 7, and 2. Then I deallocate those one by one just to verify what is supposed to be happening is happening. I know you programmed it to do that, so it seems like you don't need to check it, but there's this expression that I like and my wife hates called "there's many a slip twixt the cup and the lip," and it's really true in programming. It's supposedly about some character from the Homeric saga who it was foretold would die before he could ever drink from his vineyards again, but he makes it home from Troy, and he's about to have his first sip of wine from his own vineyard, at which point he could probably relax about dying, but then a servant comes in and says that there's a wild boar loose in the arboreum or something. And he goes out there and of course he gets killed. Many a trick, many a slip? Yeah, it's a disgusting phrase. Don't use it. So P0 has been deallocated. Now we are allocating 2 pages to P1. So what does that look like? Just allocating page 2. Remember, these things are just getting popped off the free list. So if I'd printed out the free list, we could see these things disappearing from the free list. The reason P1 is allocated page 2 is just because that's being popped off the free list, and you could look up at the free list and you could see that 2 has just been put back on, I guess. Yeah, oh, that's a good point. When you deallocate these pages, you need to put these back on the free list, don't you? Yeah, so it must be that 5 gets put back on first, then 7 gets put back on, then 2 gets put back on. So 2 gets popped off for this guy, and the page table now becomes 0 uh, points to 2 and 1 points to 7. Okay, and P0 is dead, but there's no point in redrawing all this stuff, so we could just call it P1. And what does P1 do? He actually does do something. So he sets 1, 2 to D. So here's 1, 0, 1, 2 is D. And he sets 1, 0 to E. So at least that's what he thinks he does. But what it actually does is over here on page 7, so here's page 6, so here's page 7, he sets the 0th entry to E and the second entry to D. Okay. And then what happens is P2 gets created and allocated 1 page. And that is reflected on this line right here. And now you get to see what is so crazy about the way I've decided to do the page table. If you want to do if you'd rather do a dictionary of page tables with the process name associating it to its page table entry in the dictionary, that might be more simple than what I've decided to do. So I allocate page 5 to process 2, and so what that means is that there's some page 2 here, but this is actually the 0th page of P2. And so P2 has some offset, which I store in the thing that I call the offset dictionary. That offset is 0, 1, 2, and that means that P2's pages begin at entry 2 in the page table. And so that is associated with 5, okay? And that's what this statement did, the creation of P2. Now P1 sets 0, 0 to F. So he thinks that, P1 thinks that he puts F here, but what P1 actually does is 0 is associated with 2, so there are 4 slots here, and he actually puts F on page 2, displacement 0, or the first one, whatever you want to call it. Now we create finally P3, which wants 4 pages, and that is happening here. So P3, here P3's offset in the offset dictionary is set to be 3, and so P3's page 0 gets associated with page 8, P3's page 4 gets associated with real page 6, and P3's page 0, this is a 4, obviously, that's a 4. P3's page 3 gets associated with real page 0. Alright, and then, so the way I've done things, if P2 were to be deleted, then I would have to remove this from the page table, and everything would get shifted up by 1, and you have to remember to correct the offsets too when you do that. And you also have to remember to add empty strings onto the end so that it remains a constant length. You're thinking, yeah. Okay, so now I print out the main memory by page. Let's just see that it looks the way it's supposed to. So we've got our picture that we've drawn of what the output should be. By the way, this is how you debug your own program. You know, you've got to just do the hard work of looking through. So it should be that page 5 says BC, and here it is, page 5 says BC. And it should be that page 2 says F, and here it is, page 2 says F. And page 7 says ED, and page 7 says ED. But what does the fox say? My wife just showed me that the other day. Have you seen the video, What Does the Fox Say? You should watch it right now. Um, and now at the end, I print out the pages, and then this is just the raw memory, and so this is what it looks like if you don't organize it into pages. Print out what the page table looks like. Okay, so that's what the page table looks like. Is that what our page table looks like? Let's see. So our page table says 2, 7. Oh, but I deleted this. Why did I do that? Can I get it back? I think so, yeah. So 275, and this says 275 860. 860 is right. Why is there a 9 on the end? Did it allocate more than I thought? So P3 allocated how many? P3 allocated 4 pages. So I just forgot to write that. You guys are probably screaming at me the whole time actually to do that. So that is supposed to be there. And this is my offset dictionary. And so you can see that the offset of P2 is 2, like we said, and the offset of P3 is 3. The offset of P1 is 0. I didn't write that here. And I've got the page allocation dictionary. Oh, this is what I use to keep track of how many pages has been allocated to each process. And I need that because I did the page table the hard way. So if P2 gets deleted, I need to know how many pages he owns so that I can remove exactly that many from the page table. And here's the final state of the free list. Right now there are 3 pages that are free, and they're exactly those. So I guess I'm almost done with the explanation. Like I said, there are more input and output files, and I'll give you those in pairs. And the way you can do it is, I'll give you like the short activity.txt, activity.txt, and there's one called medium activity.txt. And when you look through the sample output files, you can just look here and see what the input file was, and then you can know what that corresponded to. So when you write your program, you need to get the same things here in main memory, or your program at the very least needs to make sense. And it would be nice if your program, when it had the same initial free list, also produced the same effect in main memory. That would make it easier for both of us to see what's going on. So let me pause it for a second and see if there's anything else we need to see in the code. So I thought I might as well show you this part. This is just the main loop of the whole thing. You can see everything is factored into subroutines. So the activity is just open the file name, and these things come line by line like this. And I reverse it so that when I pop, I want to be able to pop to get the first one, and so I have to reverse it to make that true. Then I get the current activity, and if you split it, then the 0th thing is the activity. That's because in this really simple language, the command always comes first. So that tells you create, set, destroy. And then you branch on those 3 possibilities and then call some function that takes care of the details. So this is the whole thing. You just need to write these 3 functions. And that's all. And I assume we're going to talk about this a lot, and email me or catch me some other time. And when should this be due? Definitely after Thanksgiving. I wish you could see this calendar. Does this thing pop out? No. But what about this? Quit cal. So there's November. Definitely don't want it to be due in November, actually. Can we do cal 12 2014? Is it that smart? You stupid thing. Cal 12. Oh my god. What is that? Probably 2012. Man, we've really opened up a can of worms here. So let's go to Cal 14. Oh, you know what this is? This isn't 2012. This is the year 12 AD. And it tells you what nerds the Unix people are. So let's look at 2014. And here we are, it's November 17th, and this is the final exam. If we did 2 weeks, then it would be due on Monday, and maybe more than 2 weeks. How about December the 3rd? That's a little bit more than 2 weeks, and we can talk about it in class, and then it'll be due in 2 weeks. Okay, so let's have it be due on December 3rd, and that's all. Bye. See you later.